Hello everyone. We'll be discussing the code that we have created for our breast cancer classification. Here we have used the second data set, which is the breast cancer diagnosis data set, which is taken from Yugoslavia. Let me just move on to the code itself. Now, firstly, what we did is we imported NumPy and imported pandas. Then we read the CSV file which we had on the system. So here I have the CSV file installed. Then I just wanted to observe the data, how it looked like. So already we can see that the data has one, two, three, four, five, six variables, which is mean radius, mean texture, mean perimeter, mean area, mean smoothness, and diagnosis. Diagnosis would be our uh, dependent variable, and the rest of them would be independent variables for regression analysis and the other classification models. So this is just some basic data exploration wherein I wanted to know the shape. So we have 569 records of patients with like six variables, six features. Also, thing to note is that the data set is already clean. So because it doesn't have any outliers or anything, but still, we just wanted to know how it looked like, whether it had any nulls. So we went on to look at the nulls. Then we checked for duplicates. Further moving on, we imported matplotlib and seaborn to plot basic statistics or describe the data. So we wanted to see the distribution of diagnosis. So one means that the patient has cancer, breast cancer. Zero means that the patient does not have breast cancer. So over here we can see that this data set has 350 people who are having breast cancer, approximately 350 people are having breast cancer, and about just over 200 people not having breast cancer. Now we built some histograms for the same, wherein we wanted to see the distribution for across mean radius and all the other variables. So now we also wanted to check outliers that we have, if we had any, and we do have some outliers for mean radius, for everything. In fact, for mean area, we have the highest outliers, and for diagnosis, there's just nothing because it's just 0 and 1. So we wanted to check the correlation between variables, and we wanted to better relate that with the heat map. So we related that with the heat map, and we got to know that mean area is highly correlated, positively correlated with mean radius. And again, mean perimeter is uh, highly strongly has a strong positive correlation with the mean area. And there's some negative correlations too. So like diagnosis with mean perimeter, so they have a strong negative correlation, and mean area with respect to diagnosis is also a strong negative correlation along with mean radius as well. So that was the insight we got from that. Next, we made some pair plots, and we wanted to see the distribution or the scatters of zeros and ones. So as we can perfectly see, this relates to the correlation that we had with the data, where a mean perimeter and mean radius, as we saw, was strongly correlated. So the lesser the mean perimeter is and the radius is, there are chances for people having cancer. One means they have cancer, and the higher the perimeter or the radius is, that means that people don't have cancer according to this database data set. Now, so we wanted to try and see the classifications. So our six classifications for the study. So for that, we had to import learn, and had to import logistic regressions, standard scalar, because we had to standardize the data, obviously. Um, we then set dependent and independent variables. So diagnosis was the dependent variable, y, and x was the independent variables which are not related to each other. Now we just wanted to see the sample of each of the observations. Then we split the data. So training set would be 80% and the test set would be 20% of the data, and random state was set to be 42 as standard default according to industry standards. Then we wanted to apply standard scaler to standardize the data, wherein each and every observation was uh, standardized by applying the z-scores, the formula where x is the original feature value, mu is the mean of the feature that is just subtracted, and then the calculation of that is divided by the standard deviation of the particular feature to achieve standardization for each particular record respective to that variable or the feature. Then we saw, then we applied standard scaler. Then we started to test the classification model. So we began with the logistic regression model. Um, Here we have set um, the y predictor, and we set the model and we made the model fit according to the training data set. So the model got trained. Now, firstly, we displayed the accuracy. Without hypertuning, it was 93.85, which is quite high already. Secondly, we hypertuned it. So over here, let's just go down to the result. Here we can see the accuracy got up to 94.74. And the best parameters were liblinear, that is the solver method over here, as you can see. Um, the regularization strength was 0.01, 0.1, 1, 10, 100. So in factors of 10, that means that the key folds which we used was 10 for each and every study for standardizing. Now, here we made the graph for feature importance in logistic regression. So which features were most important for this particular logistic regression study. Here we found out that the mean smoothness, it was highly coefficient, so it was statistically significant to the study compared to the other features. But this cannot be true because a tumor cannot be measured that way. So I was like, let's just move on to other models. So we did the same. So we calculated the confusion matrix for it, and this was the output for the confusion matrix. Moving on, the naive Bayes classifier, that's the Gaussian distribution. So again, we trained the model and we made the predictions. Then for the classification, I built the report over here, as you can see. But firstly, it was showing a precision of 1, like, uh, and the weighted average was around 93-94%, which is quite high again. But once we applied hypertuning parameters, so we could just use variable smoothing, and we set up grid search in order to make sure that hypertuning was done for the parameters. Um, then we got to know that the accuracy was 93.86, which is again pretty high. And it also found out the best parameters for us. Moving on, we have the confusion matrix for the same. Knife base doesn't really have a feature importance, so because it doesn't rely on features, it relies more on the clusters itself. So now moving on to k nearest neighbors. So k nearest neighbors, again KNN classification. Initially we got a 93.86, again the same thing as naive Bayes after hypertuning. But after hypertuning, we got to know using grid search and everything that the accuracy fell down, and we found out that Euclidean distance was a good metric under parameters. n neighbors equal to 9, which is k minus 1, k was 10, and the weights were distant. So that is something that we found were the best parameters for this particular study. Um, Moving on, we calculated the permutation feature importance. Now here, this particular model took emphasis for mean area compared to mean perimeter, mean texture, and mean radius. And next, we built the k nearest neighbors confusion matrix. Um, Moreover, we moved on to random forest, which is the best classifier for both the data sets. So and it took a lot of time to run, so it took into account every single type of variable and its behaviors. Accuracy that it achieved initially was 94.74, which is the highest. After we hyper-tuned the random forest classifier a bit, um, we set on and we ensured that uh, the parameters were the minimum sample leaves were 1, sample split was 2, n estimators were 100, after which we got an accuracy, the same accuracy, 94.74, still very good. Um, but here comes the fun part. For the feature importance of random forest, uh, it took into account every single variable, and it took mean perimeter, mean area, mean radius, mean texture of the tumor, and the mean smoothness. So the order of importance is diminishing with each variable. However, it has taken into account every single variable, um, and it's giving justice to the classification. So that's why we feel that it's the best classifier out of the rest of the six. We computed the confusion matrix for it, and this was the output. Moreover, we moved on to the decision tree classifier, so where you build decision trees and you come off with leaves at the end, which is the final stage of the framework of the tree. Um, so initially we got an accuracy of 90.35, not bad, but could be better according to the other models that we've seen. And after we hyper-tuned it a bit, again setting these leaves and split, and we gave Ginian entropy as the criterion, and max features were included, even log as well as square root was included. We even used grid search to sort of tune the hyperparameters. Again, accuracy remained the same. So nothing major, but it's the least performing classifier, but still 90% is not that bad. Um, for feature importance, again, it takes mean perimeter into huge account compared to the other variables. It's not giving justice, it's not giving proper weightage. Um, So that's why the accuracy is less. Confusion matrix for the decision tree classifier is over here. And we are moving forward to the last classifier of our classification model study for breast cancer, which is gradient boosting. Now, for gradient boosting, what we did was we loaded the data set and we made sure that we ran the model. I mean, an initial accuracy of the model was 94.74, same as random forest, pretty close. However, once we hyper-tuned the gradient boosting classifier with the same sort of criteria for uh, random forest that we have set, and we set up grid search again to hyper-tune parameters, accuracy remained the same. Now, feature importance, again, gradient boosting had took features perfectly, but it this time it took perimeter and area as the two highest features which were having huge importance in the classification, and it sort of overfitted, you could say. Possible overfitting is there uh, that we could analyze based on the past data. Now, and it's not giving enough justice to the other features again. So that's why we feel that even gradient boosting has its flaws. We built the confusion matrix for it, and at the end, what we did was we wanted to compare each and every metric, and we came out with the best possible um, score, and we wanted to rate the models, right? So these are the ratings for each model based on accuracy, precision, recall, F1 score, and mean CV score. However, the best model by all of the parameters was random forest, and there's no surprise because of the reasons we mentioned. Now, lastly, precision and recall curves for uh, the classification models are over here. This is the code for it. So here, as you can see, it is explained in our presentation as well. So please refer to that. This is the ROC curve for the same, and overall random forest is the best classifier for both the data sets. Over here we have just displayed one data set that is into picture, but we have worked on two data sets and we have two separate codes for it. So we'll be submitting that as part of our submission. Thank you really very much. Have a great day. See ya. Bye.